We ended the last video set by describing a confidence interval as the result of a process that is designed to find the population mean a majority of the time, X% of the time. And that doesn't mean that any individual confidence interval will find the mean X% of the time. The population mean is either in there or it's not in there, and we don't know if it is. But what it does mean is that if I consistently sample in the same way from the population and I look at a set of confidence intervals, X% of the confidence intervals in that set should contain the population mean. And the whole point of the confidence interval is to pare down the space in which we look for the population mean, which is an important concept that we're going to start with today because often we have an opinion about what the population mean could be. So there's a belief about what the population mean is, and we can see whether or not that particular number is in a confidence interval that we made, but if it isn't, what does that say for what we think? And this leads to the notion of what's called hypothesis testing. Now, hypothesis testing is a key component of ECON 3402 and is again a key component of ECON 3406. So it's something that we do in the first two parts of this class. The first third of this class is almost exclusively hypothesis testing, with the exception of the probability that we've already discussed. The second part of this class is also hypothesis testing, but we're going to expand kind of the types of hypotheses that we can look at and the data that we can use. But often we have something very specific that we would like to learn about the data set. So suppose you buy a restaurant that has forced to close because of COVID-19. What you might like to have some idea about is the historical revenue of the restaurant. So when you purchase the restaurant from the owner of the restaurant, you would really like to look at the books. And you may not get a chance to look at them fully until after you make the purchase. You may be relying on a claim from the owner. And so what you could do to learn about the past revenues or the past average is, well, once you open the restaurant, you'll have new data, but you can also look at the past data to look at that average. And this is valuable information to know as it impacts the profitability of the business. So there's a claim about what the revenues were, and you'd really like to get some data to see if that claim is reasonable. That claim we can think of as a hypothesis. It's a testable claim. That's the definition of a hypothesis. And there are always two types of hypotheses, a null and an alternative. And I like to think of the null as more of a default position. So if I have no reason to think anything else, this was what might be true. The null is about the population mean mu. At least that's where we're starting in this class. We'll have other nulls as this class moves along, but we're going to start with the null about the population mean mu, and we use H sub O to denote the null hypothesis. So if you believe that the mean is some specific number, then the null is that mu is equal to that number. The alternative is what might be true instead. So I like to think of a hypothesis as just setting up two different categories of possibility. In one category, the mean is some number, the mean is less than or equal to some number, the mean is greater than or equal to some number. But there's always some specific number that the mean is equal to, and that's part of, or could be the entire null. The alternative is everything else. So if the mean is not equal to that specific number, then that's the alternative. Right now as I make these slides, I'm drinking a Diet Dr. Pepper. And there's a claim about the weight of the can on the Diet Dr. Pepper can. It says 12 fluid ounces. That is a reasonable null hypothesis that the mean is 12 fluid ounces. Well, it either is or it isn't. If it isn't, if the data indicate that it isn't, that supports an alternative. If it is, that supports a null. But there are only two possibilities. It either is 12 ounces or it isn't 12 ounces. If I think the makers of Diet Dr. Pepper are shortchanging me, then maybe the mean is less than or equal to 12 fluid ounces. That's one possibility. If it's not less than or equal to, it must be greater. And so when we construct a hypothesis, we're really constructing just two categories. Their data either support being in one category or they support being in the other category. And when we're trying to figure out what a hypothesis is, we always start with the alternative hypothesis. So on this slide, we had some information about one-sided and two-sided hypotheses, but we always start by trying to figure out what the alternative is, knowing that if you're not in the alternative, you must be in the null by default. And we can always figure out the alternative hypothesis from information in a problem. So let's take a look at the first of three types of hypotheses that we're going to be examining today. And this is what's called a one-sided right hypothesis. So one-sided means that the alternative is on one side of the claimed mean. Right, that side is to the right, it's bigger than. And one-sided right refers to an alternative hypothesis. So suppose we're examining from a problem whether or not the mean is more than 10. So maybe that's the number of minutes that you're watching these videos. And I want to see whether or not you're watching more than 10 minutes. That more than is a context clue. But what is it a context clue about? The alternative hypothesis. So if you look at that, mu is the symbol for the population mean. 10 is the number that's of interest. More than is a context clue that tells me, hey, I'm only looking on one side of 10, and I'm looking to the right of 10. So things like 11, 12, 13 count, but things like 7, 6, and 5, they don't count. So that's established from the problem. When I read, we're examining whether or not the mean is more than 10, I write down HA, mu, greater than 10. That's what you see here in blue. Now, if it's not greater than 10, it's part of the null. What's not greater than 10? 10. You see the red dot in the middle is part of the null. That's the equal sign. What about less than? Also part of the null. That's to the left of 10. So you're either to the right of 10, which is established in the problem as the alternative, or you're to the left of 10, or you're equal to 10, and both of those are the null. When looking to figure out the hypothesis as part of a problem, I look for the following context clues. I look for greater than, higher, above, larger than, increase, biased upward, anything that indicates higher. That language is telling me the specific direction of the alternative hypothesis, and it's telling me that the picture I'm making, the number may change, but I will have something blue to the right of the number, and that's the alternative. And if it's not in the alternative, it's in the null. So if I do not see these context clues, then I do not have a one-sided right hypothesis. And one-sided right, just to be clear, is about the alternative. So on this previous slide, when I said start with the alternative, in a problem, I might be examining whether or not the mean is more than 10. That is a description of the alternative. It's telling me the blue, you write the blue down first, then because I've written down this mu greater than 10, if it's not greater than 10, it's less than, that's everything to the left. 10's also included because 10 is not greater than 10. Now let's look at a one-sided left hypothesis. Suppose I'm examining whether or not the mean is less than 10. Still one side, only looking less than 10, not looking greater, just left. Less than 10, 9, 7, 6, 2, -1. All of those are less than 10. That's everything to the left in blue. That is a description, again, of the alternative. So mu less than 10. Less than is a context clue. Other context clues: lower, below, smaller than, decrease, bias downward. Anything that indicates lower is a one-sided left context clue. And if it's not lower, then it's above, greater than. So if I'm not less than 10, I'm greater than 10. That's to the right, and that's part of the null. And I could be equal to 10. That's also part of the null. So if I do not see a one-sided left context clue in a problem, then again, this is not the right set. So we set up two different types of alternatives so far. We have a one-sided right, greater than. We have a one-sided left, less than. If it's not one-sided, it's two-sided. So maybe I just want to see whether or not the mean is 10. So 10 is the number listed in the middle. That is the null. Is not is everything else. Everything else. Not equal to 10 over here. Not equal to 10 over here. 9.9, that's not 10, that's in the blue. 73, not 10, it's in the blue. We established the not equal 10 from the problem. Other clues: is an indication that the alternative is two-sided. There is always an equal sign in the null. So if you look at all three of these pictures, you see an equal sign here and here and here. The null is always going to have this red dot in the middle. Well, you can draw whatever color you want, but I use red. There's always an equal sign for the null. There's never an equal sign in the alternative. If I see something like is not, claim is reasonable, statistically different from, none of those indicate direction. Those indicate that I'm looking at a picture like this. And so here is the hypothesis on the number line. Before we go any further, these are claims that we're making about the value of a population mean. We don't particularly care what the result is. So I never like to think of it as I'm trying to prove the alternative or I'm trying to disprove the null. I think of it more as I don't care what the null and the alternative are. I'm trying to set up a framework that is the most descriptive of what could be going on. And then I just take the data and see what happens. So I take the data and try to figure out if it's more reasonable that I'm in the blue or if it's more reasonable that I'm in the red in all of these circumstances. And I have a specific process for doing it, but you could think of it more generally like a jury trial. So you base the result of the trial based on what's in the courtroom, what's been said. So, you're either guilty or you're not guilty. And the evidence should lead you in one direction or the other. And if you think of the goal of a juror, you don't want the juror to have an opinion going in. So likewise with the hypothesis, I set up a hypothesis. Now maybe I have some practical interest in the result, but hopefully I just take the data and see whether I'm in the blue or the red. I don't try to get into one area or the other. Okay, so a key component to this class is being able to figure out what a hypothesis should be from the information in the problem. So let's look at this problem. Suppose that the director of a state agency believes that the starting salary for clerical workers is less than $25,000 a year. I start with the alternative. I should write mu less than 25,000. For the null, I should write mu greater than or equal to 25,000. So this less than is a context clue that tells me an alternative. The null is everything else. And maybe in stats 1 you just used equal in the null, but I would like us to kind of move toward using greater than or equal if we can. So this is a one-sided left alternative hypothesis. Now here's another problem. Let's say we have an internal report for a chain of national oil change places like Jiffy Lube or Express Oil, etc. And they recommend changes every 4,000 miles, and they want to see if customers behave differently. So differently doesn't mean bigger. So it could be like my parents, and they'll get their oil changed every 3,000 miles, or it could be like me, and I do every 5,000. Alternative mean not equal to 4,000. Null mean equal to 4,000. Okay, so on this hypothesis formulation slide, I really want us to take a solid look and seeing, did we find the context clues when we were going over this? Let's relate hypotheses to confidence intervals. So I think big picture here is, let's go back to these pictures over here. If I draw a confidence interval around some area out here and I don't capture the red dot, I should think, goodness, is the red dot really a reasonable approximation for the population mean? And what I should conclude is probably not. It doesn't mean that is definitely not the population mean. It just means it's not that likely to be the population mean. So if the null is outside the confidence interval, I should think, gosh, the only goal of the confidence interval was to capture the population mean. That is literally all it is trying to do. There's nothing else it's trying to do. So if you didn't capture the null, I would kind of have to wonder whether or not the null is a reasonable guess for the population mean. Now, the confidence interval process will capture the true mean X% of the time. And I don't know whether the claim mean is the true mean. All I can do is collect data and do a hypothesis test. Likewise, if the red dot happens to fall in the confidence interval, it does not necessarily mean that is the true population mean. It just means I don't have any evidence to think otherwise. And so we can kind of look at this through the context of what's called a p-value. A p-value is the probability that we would observe our data if the null were true. So if the null were true, what is the probability of getting our sample? Lower p-values, 0.1, 0.05, 0.01, 10%, 5%, 1%. All of a sudden, if our data is pretty unlikely, if the null were true, what I want to guard against thinking is, hey, I just got this really unlikely sample, but the null is true. What I should be thinking instead is the null reasonable? Is it not? Higher p-values, null more likely to be true. So the sample is closer to the population mean if the population mean is the null. Okay, so how this works in our class is that we could construct a confidence interval every single time, but it can be obnoxious to do that. So what we do instead is we just try to find a measure of location. Where is our data relative to the null? And this is called a test statistic. I explicitly compare my sample of data to whatever the red dot is in the null. And I divide by the standard deviation over the square root of the sample size. So what I do is construct something that looks almost identical to, it is identical to this z-score here for the sampling distribution. The difference is that I interpret this now in the context of testing a hypothesis with a test statistic. I compare the test statistic to what are called critical values. So how far must my data be from the null for me to start to think the null is not likely to be true anymore? Well, I have to have some objective process for thinking about this, and this objective process means I compare whatever my test statistic, how the test statistic describes the location of my data, I compare it to some cutoffs where once I blow past the cutoffs, I think, gosh, this is really getting to be far away from the null. Maybe the null is not that likely to be true anymore. I look at three specific cutoffs corresponding to p-values of 0.1, 10%, 0.05, 5%, 0.01, 1%, And I look at critical values that we've used previously. So we used 1.65, 1.96, and 2.58 to make confidence intervals, and those are the critical values I use for two-sided hypotheses. Then I use other critical values for one-sided hypotheses, and I'll describe why here in a minute. Okay, but let's look at the visual idea behind the two-sided values first. If the sample is exactly equal to the null, I'm right here in the middle at 0. As my sample gets further and further away from the null, whatever the null is, I start to be possibly in the red, the yellow, and the blue. And these 1.65, 1.96, and 2.58 indicate that my sample is X standard deviations away from the null. And the further away it is, the less likely I think the null is to be true. With the one-sided right hypothesis, the alternative is the mean is greater than some number. I've got to get a number larger than the claim to count as evidence. So let's say that I believe that the mean is greater than 10. That's my alternative. Well, if I get, minus 74, that's pretty far away from 10, but it's certainly not greater than 10. So anything over here doesn't count. So anything to the left of the claim doesn't count. So to the right of the claim is the only possible data that could count as support of the alternative. And if you take a look in the Z table at 1.28, let's have a look there. 1.2 row, 0.08 column. I have about 90%. 90% of the time I'm going to get a z-score smaller than 1.28. That's the justification for this first cutoff. 95% of the time I'm going to get something smaller than 1.65. That's the justification for that cutoff. And then 99% of the time I'm going to get something smaller than 2.33. That's the justification for this last cutoff. So the cutoffs just force all the data to be to the left of the, not the mean, but they force the data to be the left to count as evidence for the null. So I can't have data to the right. And it's in reverse. If I have a one-sided left hypothesis, we just flip the signs. Okay, so these are the steps that we use to test a hypothesis. We're going to construct a test statistic, compare it to a critical value, and state the findings. We're going to examine how to make a test statistic in the next set of slides.